And actually, thanks for even coming today. Okay, so this talk will be actually, you'll see part history, part propaganda. And it's quite opposite that it should be given here, as you will see, actually. So let me start with the history. Okay, so in 83-84 there was an extraordinary year here with a team. It was on automorphic forms, and the topic has just exploded with largely due to Langlands' work on base change and the progress on the trace formula. And Arthur and I, Jim Arthur, were present, and we participated in the different seminars, and we found that we had ideas on opposite sides to attack the problem of extending Langlands' base change results to GLN, and so that started a collaboration which we pursued until 87. I think we had the final manuscript in 87, and it was published in 89. And so we did base change for GLN. So let me start with one of the results. So the fields will be here generally a number fields. So let me consider E over F a cyclic extension of number fields. So once and for all, I'll write sigma for the Galois group. And I will choose a generator, say a small sigma, of this cyclic group. D will be the order. And in such a situation, we have an operation on automorphic forms, or rather automorphic representations. So here we start with a representation pi f, which is a cuspidal representation of GLN AF. And there is an operation which I call restriction, and which from pi f produces a representation pi e, which is, so again I'll denote this as the restriction from f to e of pi f. So this is a representation, not always cuspidal, but the relation with some cuspidal representation can be easily described. In any case, it's an automorphic representation of GLN, but now over the adels of the field extension. Okay. Since most people have really made efforts here to explain the basics, let me recall even the definition of base change. So this is often called base change, but the term is vague. And in fact, the best way to think about it is to remember that sometimes automorphic representations are associated to representations of the Galois groups. And when this is the case, this is just restriction of a Galois representation from the absolute Galois group of F for some algebraic closure to the algebraic Galois group of E. So that's one way of thinking about it. And let me actually give an explicit definition. You have your field extension E over F, which is cyclic. And to define this, it's enough to define the going up operation in each step of a prime tower for the cyclic extension. And so if D is prime, then explicitly the base change is defined by the Hecke matrices. And since I'm going to need that later anyway, let me just say one word more about what the Hecke matrices are. So we have, for example, F. We have a representation pi F, automorphic. By definition, it's an infinite tensor product over all primes of F, so pi V. And recall also that for almost all finite primes V, then pi V is unramified. It has vectors fixed by the maximal compact subgroup. And that implies that it has a Hecke matrix. So pi V, in fact, when it is unramified, is associated bijectively to a matrix which I'll call T pi V. And this is a diagonal matrix of order n, actually defined modulo permutation. Okay. So in terms of Hecke matrices, then you just translate the operation of restriction of vague group representations. And then suppose now I have E over F, a prime extension. Then the datum is the representation below. And we want to define T pi E W for W unramified. And that's given by the formula which follows. We are going to take the matrix of the given representation in the split case, and we are going to take the diff power in the inert case. Okay. Let me just say in words that there are strong rigidity theorems in this situation, which imply that if you have a cuspidal representation, in fact, if you know the Hecke matrices at almost all primes, then you know the representation. It's uniquely determined. Okay. So I have given you an idea of what this restriction was, and in particular, if you think of the Galois description when it exists, you see that when a representation on over E is obtained that way, it is stable by Galois action. So, fact, if pi E comes from F by base change, then you'll have that pi E is equivalent to pi E sigma, where I let the element sigma in the Galois group act in an obvious way by composition. Now, one theorem which was in our book page 217. So theorem 1, I think everybody can see here, right? So theorem 1, assume conversely that pi E is a cuspidal representation so it's fixed by sigma in the obvious way described here, then there exists a representation pi f. So in that case, if I go down, if I start with cuspidal, it will be cuspidal. Of course, of GLN AF, and such that, well, with my notation, pi e should be the restriction of pi f. Okay, so I think I said 217. So this is in my book with Jim Arthur, quite at the end. But unfortunately, this proof is false. I don't think there is any serious mistake before in the book. And it is false for the following reason. By the way, since this is a common book, I cannot tell you who wrote that part. It's false for the following reason. Suppose, for example, that n is just a product of two primes, PL. And so I'm going to study the extension by dévissage. I have my extension E. And let me stick to the choices I've made here. I have first an extension E of degree L, and then I have another extension here of degree P. And with my notations, the Galois group here for the intermediate, the above extension will be sigma P. And of course, here the Galois group will be given by the image of sigma acting on E1. Okay. So in this situation, the theorem, by the way, the theorem is indeed correctly proved for D prime. So and so certainly we can start with pi E here, and then we get a representation pi E1. This is correct, but there is another fact. It is that already in the case of a prime extension, and this is obvious if you think of the representation theory, the representation below is not unique here. So if pi E is given, then pi E1 is determined modulo twist by powers of the character given by class field theory, epsilon here E over E1, character of A star E1. Okay. The consequence of this is that, okay, you can descend here, but you do not know what representation you have to choose to continue the descent. And in purely automorphic terms, there is no way to choose. I mean, there is no way to distinguish amongst the elements of this orbit.
So should that n be D is here?
Should
that n be D? D is the degree of the...
where?
Example n.
And, oh, this is D, I'm sorry, yes. Oh, thank you, thanks. So that's the degree of the extension. Okay, so I descend here, but here I cannot choose the good representation. There is only one which will be obtained by restriction from the one I descend, and then I cannot continue the descent. Okay, so that's the way things stood after the publication of the book. But first of all, that mistake was fairly easily corrected. And two, actually, I think it was a productive mistake. So in fact, first of all, although the proof was written that way in our third chapter, if you look at the book, chapters 1 and 2, in particular, the use of the twisted trace formula, you'll see that the assumption of prime degree is not made. And if you rewrite chapter 3, where this occurs using the trace formula for an arbitrary cyclic extension, you can easily patch this up. So rewrite chapter 3 correctly using the previous results. And in fact, that was done by Labesse. Labesse gives actually easier proofs of our results in terms of the trace formula. That's in the published the paper here. And but what is fortunate for us here is that Lapide and Rogawski actually pointed out the mistake, and they indicated, independently of the previous remarks, they indicated a way to remediate it, and they did that for GL2. So I'm going to say more about that. And this then led to an interesting result of Rajan. So that's where I want to get now. So now I want to say something more about the fortunate character of the mistake. And from my sketch of the description of the problem here, you can see that, in fact, if we had a full Galois representation given extending the representation here, it's fairly clear that at each step we could actually choose consistently the descents and then finally get the representation below. And this was noticed by Michael Harris. Not with the kind of Galois representations I was using here, but with L-adic representations. And the fact that you can choose descent that way plays an important role in the proof of the local Langlands conjecture. In fact, it's incorporated in the final book with Richard Taylor. Okay, so actually, I don't regret that we made this mistake, but now I want to say a little more about the approach of Lapide and Rogawski, because that's the one in which I am interested in today. So, yeah, so Lapide, Rogawski. So rather strangely, they showed that you could complete this proof of base change if you prove the negative result. So in base change, we are interested in this equation. Pi A is stable by sigma. But more generally, we can consider a class field, a character omega of the ideal class group. And once for all, I'll write CE or CF for these groups. And rather than this, we can try to find a representation pi E which satisfies that its Galois conjugate is isomorphic to pi E twisted by the character omega. So of course omega equal to 1 is base change. And what Lapide Rogawski showed is that for some characters omega here, this equation should be impossible. So let's consider the following statement. Theorem A. Assume our character omega is given, but such that if we restrict it to the ideal class group of CF, this is equal to our class field character epsilon over E over F. And then the theorem is simple. There is no cuspidal representation. Actually, let me erase this because the thing to underline is cuspidal. There is no cuspidal representation of GLN AE, verifying the equation here. Okay. So I write theorem, but actually that's what I want to prove today. And what did Lapid and Rogawski do at the time? As I said, they proved it for GL2. So prove this for n equal to 2. And more important for us, they proved that it implied theorem 1. Okay. So in particular, they completed the proof for theorem 1 for GL2. Personally, I find these non-existent statements interesting as such, but in fact, we wanted to prove it. I didn't say actually, I wrote this because I knew I would forget it, but this is all common work with the CS Rajan. And we wanted to prove this because Rajan drew some implications from this theorem. So that's theorem 2. Which now is completely proven then. We are in this cyclic situation. And we give ourselves, I'm sorry. What Rajan did is that assuming this, then he was able to extend the descent theorem to the solvable case. So let me take a solvable extension. And then I take, as before, a cuspidal representation of GLN stable by the Galois group, invariant by Galois of E over F. So if you think in terms of the Galois representations, you'll see that it will not always descend. But something a little weaker is true. Then there exists a character chi-e of the ideal class group, invariant by the Galois group, and such that pi E tensor chi-e is obtained by base change, is the restriction of pi f for some pi f. Of course, it will be cuspidal. Okay. So I'm not going to say anything about Rajan's previous proof. What I want to say something about today is the proof of theorem A. Now, of course, in the cyclic case, you see immediately that theorem 2 implies theorem 1 because the character Ke being invariant is obtained by composition with the norm from a character of the small field. So, two idea of proof. So we have this problem pi e sigma equivalent to pi e twisted by omega, omega being as I explained, and such a problem can be treated using the trace formula. So for that we consider a space of automorphic forms, L2 automorphic forms, in fact, AE, and that will be L2 discrete of G of let me write a G naught for the algebraic G group GLN. Okay, so G naught of AE divided by G naught of E, and for good measure, actually the term is exact. To have a finite measure, we quotient by AG. AG is just or AG naught, say. AG naught is R star plus embedded diagonally everywhere, diagonally in the groups at the real places and at all places. Okay. The importance is that we have finite measure, and then of course the Hecke algebra, the smooth compactly supported functions of the adelic group, acts by convolution on the right on this. Okay, so obvious in this trace form, in the space of automorphic forms, we are going to consider certain traces, and in fact we want to consider for a function phi in this big Hecke algebra, we consider the trace of let me write first and explain afterwards. R tensor omega minus 1 of phi. So the trace is in AE. E sigma is the Galois intertwining operator. If I have a function here, I send it to its Galois conjugate. So psi is here. And well, the R is this right translation representation. And of course, I can twist it by the character. And it's fairly obvious that a cuspidal representation satisfying this equation then gives us one contribution to this trace. So the hypothetical pi e gives us one contribution to the trace. So in particular, if we want to show that these representations do not exist, it would be nice to show that this trace is simply 0. Now I have to make a remark. Ideally, the trace formula would give you a formula for the trace of the function in this space of discrete L2 automorphic forms. But Arthur's work shows that this cannot be done. You have to add some other terms. That's important for what follows. So let me write a danger sign. There is no formula. At least nobody has been able to directly write a formula for the trace of phi or whatever twisted trace like this acting in L2 discrete. You have to add other terms. That was already the case in Langlands' GL2 manuscript. So there are discrete Eisensteinian terms. I think this is fine. And I certainly want to describe those, but I want to show the ones which will matter to us in the simplest case, in the case of Lapid and Rogawski. The terms to add to get the computable trace are the following. So let's take n equal to 2, E over F quadratic. Then you see that there are some induced representation which will satisfy the symmetry question mark. You can take a representation pi E, which is pi of chi eta for 2 characters. So that's the induced representation. The induced adelic representation from the Borel. And you choose chi eta, so the equation there is satisfied. And for that, you have to take sigma chi equal to eta omega and sigma eta equal to chi omega. Now that makes sense because omega sigma is equal to 1 since omega is 0 not only on the norms but on the whole A star F. Okay. So in fact, the consequence that we have to add these singular terms of course, they are more complicated, more composite in the general case, in order to get a T-disk. And in our case, it's not T-disk of phi, it's T-disk of E sigma R tensor omega minus 1 of phi. Okay. So that's complicated, but it's totally explicit. Arthur tells you which terms you have to add. And then, of course, once we have written this, we would like to compute it. Okay. Well, now we are getting into a huge black box. And in fact, the idea now, which actually all this started in '83, was to stabilize this formula. The term is spacious here because everything is stable, but never mind. So we want to stabilize this formula. That's the accepted term, and it means we're writing this in terms of something that we don't understand anymore, any better. So T-disk of phi is going to be a sum over E of some constants. So this is just a positive rational and ST G prime disk of phi G prime. Okay. So let me just say what the data here are. So E is a set of what's called the endoscopic data. For the problem here being defined both by sigma and by omega. Phi for each element of E in particular defines a certain group G prime over F. So in particular, we can again take the trace formula for G prime. Phi G prime is a function of the same type in the Hecke algebra on G prime. Here AF. And then what else do I want to say? And then we have this ST disk of G prime, and that consists in looking at the discrete trace here, but now without the extra data, just the ordinary discrete trace, and stabilizing it in a certain way, which I will not describe because stabilization does not occur for us, the groups being always GLN. Okay, so stabilization of trace formula. Okay. Okay, so if I don't want to cheat completely, then I have to tell you a little more about endoscopy. So, in fact, the right-hand side here I said that we can think of it as a black box. Quite often you can use it that way, but in fact it is explicit. After an enormous amount of work by Langlands, Shellstadt, Kotwitz, and now a 1,300-page book by Meglin and Walsburger. So it is explicit, and to finish this lecture, I want to give an idea of what it is in our case. So we start with our group GLNE. But this is a bad way of looking at this group, because you see that when we are computing these things, we are letting sigma act, and sigma does not act by E automorphisms. So in fact, we want to look at this as an F group. So rather, we will write a G for the group obtained by restriction of scalars from GLN. That's really our group in this computation, and everything is over F. Okay. So all these data are described in the dual group, so I have to say something about the dual group. If you look first at the connected component of the dual group, here you are just adding copies, so it's going to be GLN C, and when I am on the dual side, I write simply GLN, and of course to the power G. Now we have to define, to understand the F structure on the dual group. So we'll have GLN to the D semi-direct product with the Weil group over F, and the Weil group acts by a cyclic permutation. So it acts first only by the finite quotient sigma, and sigma of G1 GD is G2, and so on, D minus 1 G1. Okay, cyclic permutation. we need another datum, which is in the problem. It's theta. So obviously enough, theta is going to be to define a theta hat. And a theta hat is given by the same formula. In particular, you see that theta hat clearly commutes with the action of the Weil group, and so somehow it's defined over F as an automorphism of the dual group. Okay. So these are our basic L group data, and now I'm going to impose on you the list of conditions of defining this mysterious is there. Okay. So an endoscopic datum is just the following set of data. So I want an element S in G star. Remember that G star is the complex group. And for that, we can look at S tilde, which is S theta, which I consider as an element of G semi-direct product theta. Theta is just the group sigma, but when I think of it as generated by the endomorphism theta. And I want that to be semi-simple. Semi-simple in the non-connected group. Okay. First datum. Second datum, I want a group G prime. That's the one which occurred in the statement there, which is connected reductive over F. The third condition is that I didn't introduce the notation. As always, LG is G hat cross WF. And I want a group G prime, which is a subgroup of LG, and which has the following properties. First of all, I want that a G prime intersected. No, I don't want to state this here. So what I want is that is to have an exact sequence 1. So okay, I should say here this is closed, and I want an exact sequence 1 G hat S tilde G prime WF 1, which is compatible with the exact sequence defining LG. I won't write it. And what is this? Well, it's essentially the centralizer of S tilde. So I want to state that as the next condition. For so G prime. Yeah. So I'm sorry. So I have an exact sequence here. This, of course, sits. This compatible. I said is compatible. This exact sequence is compatible with this one. So that means that this sits in G hat. And what the notation here says is that it's the twisted centralizer of S, or the centralizer of the element S theta in the non-connected group. Okay. So now this is well defined. And what is the relation with G prime now? Well, essentially is that this defines the L group of G prime. So precisely, G prime hat is G hat S tilde. I hope this is my notation there, yes. And the Weil actions are compatible. That's not all, because in this data you don't see the character omega so far, and of course it's crucial for us. So the last condition is the following. If you have an element GW in this non-connected group G prime, and if you form S G WS minus 1 for VS defining our datum, sorry, I have theta hat, so I should put it here. And then I want that to be equal to A W G for an element for AW should be in the center of G hat. This equation implies that then, in terms of W, it's a one co-boundary. One cocycle, I'm sorry, for the Weil group. And years ago, Langlands showed that for tori, elements of the H1 of W were associated to automorphic representations, namely characters of the ideal class group of the torus. So what we want is that AW defines omega. Not that in our case, somehow Shapiro's lemma and transfer are involved, because omega is a character of the class group over E, but we want to think of it as a character of the associated F torus. Okay, I have listed these conditions not to start immediately computing with them, but to show you that they are quite explicit, and that in fact, in a simple case like here, you can completely, absolutely compute with them. And so this leads me to the, in some sense, the main result, proposition 1. I'm back to the general notations, D, N, and so on. And the first part is exactly what we wanted. If D does not divide N, then E is equal to the empty set. So we are done. Perhaps you don't see that, but I'll quickly explain why. But of course, the example of Lapid-Rogawski for GL2 suggests that this is too simple in general. It is. So now assume that D divides N. I think I have this notation here. So N is equal to BD. And then there exists a unique. Sorry? D prime?
Is D?
No, D is arbitrary. I want to prove theorem 1 or theorem A, and it's crucial that. No, it's arbitrary. So if N is a multiple of D, then there will be an endoscopic group for that problem, a unique endoscopic datum. And in fact, I will not give you the explicit datum, which contains the description of the embedding, which is complicated, but I'll describe the resulting group. And in fact, you find that G prime is isomorphic to GL B E. In fact, the restriction of scalars, but okay. Okay, so I'm sorry.
I mean, what if
either D divides n or D does not divide n. But
only if D is prime?
no.
Oh, sorry.
Sorry.
I'm being foolish, thank you.
I've asked so many foolish questions in this conference that. Okay. So no, this is really what obtains, and I should. I feel safer under attack because I've checked it with Valls-Burger. So to finish, let me show you why we are done in the first case. And in fact, once you have seen this, you'll see that the rest is not harder. So proof in case 1, proof of theorem A in case 1. As I said, a priori, you could have some extra terms in Arthur's trace formula. So we have the hypothetic representations pi e verifying the equation, pi e cuspidal. But as I said in Arthur's work, we'll have other discrete terms. First of all, you'll have precisely the terms of Langlands-Valls-Burger, the well-known structure of the discrete spectrum for GLN, which is not necessarily prime. And so we have things associated to a decomposition A-N equal to AC, say. And you take a representation pi A. Everything is over E here. And then you form the induced representation pi A twisted by the character absolute value to the b minus 1 over 2. Then the plus, which denotes parabolic induction, pi A b minus 3 over 2, and so on, up to the opposite twist here. Okay, if you don't know that, it doesn't matter. In any case, it's an induced representation, and it certainly sits in the discrete spectrum. But there is a very strong theorem of Jacquet-Chalika saying that there is no interference. Hecke eigenvalues can't be the same for representations which are induced like this, which are sums of cuspidal representations, and a representation like ours, which is supposed to be cuspidal. Consequence, if the total sum is 0, I cannot have a cancellation between this and that. And then I'll also have, I'll give that formula essentially to finish. Possibly I could have terms which are the extra, by the way, this is still in the discrete spectrum. It's in L2, but then I have the additional Eisenstein terms of Arthur. And to finish, let me show you what these would look like in our case. These terms, when they are here, and they will be here in case 2, are of the following kind. Again, I take n equal to AC, say, and I have a representation pi 1, pi c, which are cuspidal for GL A of the adels of E. And you assume that they are permuted cyclically by Galois action. Namely, pi I sigma is isomorphic to pi I plus 1. When this can happen, you'll see that you have, times omega, of course. when this can happen, you'll see that the sum of the parabolic sum, which I just wrote, will produce a representation of the full group, which verifies the equation question mark. So, first of all, two remarks here. Again, we don't care, because in the proper case, we'll have a sum of cuspidal representations for lower groups, and we have read Jacques-Chalica, so we know this cannot happen. We do not care, but in fact, since the total sum is 0, we prove we prove that these things cannot happen. So, fact, it's a theorem which reinforces theorem A plus. This cannot occur. Beware, it cannot occur when it should not occur, namely in case 1. Now, I just want to finish with 2 words. Of course, you see what's going to happen here. There is an endoscopic contribution, but when you make the computation now completely in the L group, that determines explicitly the Hecke matrices at unramified primes. And what you do find is that all endoscopic terms are seen pulled back to the Hecke algebra of the given group, then will give you precisely things of this kind. And so they account for the discrete terms of R theorem. Okay. Okay, I think I'll stop here.